Welcome to learning OCaml. Um, well, it's maybe that's not really the correct thing to say. Maybe the correct thing to say is basically trying to learn functional programming or just programming itself, because it's hard. It's hard. So I've been trying to understand how recursion works. And yesterday I saw a wonderful example from, if I open now that tab, it's from the MIT lecture, Open Courseware. What's her name? Amanda Bell? Annabelle. Yeah, she's teaching the MIT 106, or that introductory course where they use Python. So there is one, it was very good. There is one lecture on recursion, actually two. And I saw like half of the first one. And she used an even more simple example. She used, let's go to Kitty. So here I tried to use like summing of the list, but she used that even better. Okay, I mean, I'm not saying that this is bad, but she used the example of multiplying just two numbers. 5 times 4. And you can express this with recursion. And I was kind of blown away. Wow, 5 times 4. So you can write that as 5 plus, right? 5 plus 5 times 3. And then you can write that as 5 plus 5 plus 5 times 3, 5 times 2. And then you can express that as 5 times 5 times. You see, she was saying, how would you multiply the two numbers without actually having the operation of multiplication? Like, what does that mean? The multiplication means I add 5 times to itself 4 times, right? That's basically what 5 times 4 means. And you know, you almost take it for granted. 5, you add 5 to itself, or just you add 5 4 times. So that's why we have this shorthand, 5 times 4. So 5 plus 5 plus 5 plus 5 times 1. And you see how it expands. And then 5 times 5 plus 5 plus 5 plus, and now 5 times 1. 5 times 1. I think you have to have a base case. The base case would be, yeah, you might say we are not using the multiplication. But you could say 5 times 1. Well, that's 5. Yeah, maybe I'm being nitpicky now, because if you say 5 times 1, well, how do you know what this sign means? 5 plus 5 plus 5 plus 5. So 4 times. 5 plus 1. 5 times 1. The base case is, what's the base case? What's the formula? So 5 times 1 is 5. Five, 0. Maybe you could go all the way up to 0, which is 0. Curious about this, because it's only 4 times 5, so you should stop at 5. M plus 0. Five times 1 is 5, plus 5 times 0. Well, you could do that. I think that would be actually more correct. 5 times 0. Would that make sense? 5 plus 5 plus 5 plus 5 plus 5 times 0. And 5 times 0 is 0. I'm curious if this would be more correct. More, I don't know. 5 plus 5 plus 5 plus 5 plus 0. And then you start. Actually, you start to add up here. 5 plus 5 plus 5. Right, and then 5 plus 5 plus 10. I'm not sure if you also do this sequentially, so to say. 20. And here you have it. Look at this thing of beauty. Look at it. It's so pretty. So this is what I was thinking, but you know, how do you express this as code? Right? It was such a great example. So basically what we are having here is, look at this. We have an A, right? Okay, so A is 5. That's an A. Let's do it like this so that it makes more sense. And this is a B, right? So A is 5 and B is 4. So this means this is an A, right? Because A is 5, right? That's how you get, and A is 5 plus, well, this is another A, right? A plus A times what? What's a 3? Well, 3, it's B, right? But not, how do you express 3? Well, you express it by saying 4 minus 1. But I guess it doesn't make sense, right? 4 minus 1, because how do you express 2? Well, 3 minus 1, because 4 and then 4. Maybe this is not too clear. Yeah. So we have 5 plus 5. 5 plus 5 times 3. 5 plus 5 times 3. What do I mean by this? So A plus, the formula would be A plus A times B minus 3. B minus n, because we start with some n. B minus 1. No. A plus A times B minus 1. That's completely wrong. A plus A times B minus 1. B minus 1. This would be the formula. You see? You see what's happening? So B is 4. But in this case, A is 5 plus 5 times 4 minus 1 is, if you put 4 here, you get 4 minus 1, right? Does that make sense? Well, let's make a screenshot. This would be a nice screen. All right. Right. Maybe I should yeah, I still don't know how to group things. I think visual mode, right? And yank, no, visual mode, and delete, actually. No, that was not the best. Visual mode, Look at this white space. And paste it in here. Yeah, so this is the formula. And here, what's happening here? Well, we have an F5, right? We have a 5 plus 5, that's an A, times 4 minus 1. That's what we have here, right? And then here it's gonna happen the same thing. 5 plus 5. Well, you could say times 4 minus 1. Now it's 3. Yes, now it's 3 minus 1. Three minus 1. Still, we have to count for the 5s. The expansion of 5s. Let's try to write this actually. That's our sum list. So let rec, what will we have? Let rec, because it has to call itself. So we are defining a multiplication. How do we do that? Multiplication of what? Of A and B equals what? Let rec mult AB. Let rec mult AB. So we again have to have a base case, right? If one of these, but now we won't have a list. We have A's and B's. So if one of these is a 0, maybe can we express it like if A or B equals 0? But we could have also the 0 case, then 0, right? Then 0. Else. So if A divided by B is 0, if A or B equals 0, I'm not sure if this is the, or I should use the double, because I'm expressing equality, not like an operation and the result is 0. So if A or B equals 0, then 0. That should cover our base case actually. Of, let's say, 5 times 0, because A or B will be 0, so we don't have to make actually A. Okay. Well, that means you could have also, if A or B equals 1, then what? Then A. And you will have to cover both cases. I guess it makes more sense to have it with 0, right? Do you know what I mean? If I cover the case A, okay, A or B is 0, then 0. Else, what do? We add A plus multiplication, mult A, B minus 1. Mult A, B minus 1. B minus 1. A plus mult A B minus 1. This expression has type bool, but an expression was expected of type int. Oh, if A or B are true. Yes, I'm using the OR. Well, I think, yeah, I could say like if A equals 0 or B equals 0, then 0. Maybe this would be better. Yes, if A equals 0 or B equals 0, then 0. Let's try like this. Now let's do mult AB. Well, mult 4, 5. Let's try mult 4, 5 or 5, 4. It's the same thing. It's 20 and mult 4, 5. It's 20. Let's do 12. And this. And we have our multiplication. Isn't that cool? Isn't that cool? Wait a second, I have to make a screenshot of this. It won't work now? Ah. Like this. Okay, print screen. Okay. Well, I guess, you know, you could go a step back now. That was my thought. And what if we could define everything like this? Also numbers. Then you need, I guess, the successor functions. What's a successor function? You know, like let successor let rec let rec successor of what? Successor of some n equals, well, it's that n plus successor of n. I guess that's it. Wow. So now we have our successor function. Let's try. Nope. N plus 1. Oh, look at it. Overflow. Stack overflow. Looping recursion. No. N plus 1. Successor of n plus 1. That's a successor. But this thing will, well, no, this is not correct. It's just n plus 1. What am I doing? I don't need a rec for this. Let successor n is n plus 1. And successor of 0 is 1. And successor of 1 is 2. But you could do it like successor of 0. And you get 2. Oh, now I will use a rec. Now we can use a let. Look at this. Let rec natural. Let's define our natural number. Let rec natural n equals n plus successor of n plus 1. Now, what am I doing? plus 1. It's funny, it's like, no, I should use natural. Natural n plus 1. Let rect natural n plus natural successor of n. Maybe like that. Successor of n. Really? No. Natural. Yeah, but how do you, it's still the same thing. I've basically defined, what am I doing? No, stack overflow. Yeah, I don't know what I'm trying to do. I guess I'm trying to define natural numbers, but that wouldn't work like this, right? Because we're getting a single result. I don't know what I'm trying to do. Oh, I see what I'm trying to do. Let 0 equals 0. Let 1 equals successor of 0. Let 2 equals successor of 1, but you could say successor of 0. Yeah. And let 3 equals successor of 0. And now we have 0, 1, 2, 3. You see? We have all the numbers. We have all the ints. But how would you define now addition? Like let addition of A and B equals what? How would you define addition? Well, I guess you define addition like, well, first you have to define numbers. Okay, I won't go into this now, but this is kind of, because it will take so much time. It's like a rabbit hole, you know. Once in a while you want to go down and define numbers. Yeah. So where did I stop actually? Oh, this, write a recursive function which, given a number n, calculates the sum 1 plus 2 plus 3 plus n. What is its type? We did that. Write a function power xn which raises x to the power n. Give its type. A power xn. Write a function power xn. So power xn equals, well, power xn, it's kind of similar to what we did before with the multiplication. So it's basically that number itself, x. Let's say x is 2 and the n is 3. So it's basically just the same as saying 2 times 2 times 2. That's called the power of n, of 3, the power of 3, 2 times 2 times 2. So it's taking the n time, well, power xn is, I guess, oh, we again need to have a base case. Yeah, let power xn. Power xn. Let power if what? It's incredible. I'm like, I still feel stuck with these things. Let power x n. Well, if n is 1, I guess. If n is 1, is 0, then 0. But you are actually multiplying the entire number. So if we multiply it by 0, we're going to get a 0. If n is 1, then x, actually. Yeah. Let's do it like this. If n equals 1, then x. That makes sense, right? So that means, right, when n gets to 1, so that means we'll have to get to 1, because the n could be 5. But if n is 1, then we'll just return the x, because 2 times 1 is 2. So return the x, whatever number it is. Else, oh. My son is coughing. He should be asleep now. I think he's asleep. Maybe not. He's with his mom. Okay. Else. Well, n times. No. X times. Because we have to multiply the x with itself. How many times? Well, to the power of x times power, we're going to have to call the power again. Power x n minus 1. Right. We have to take a smaller... The recursion calls itself, but always in a smaller thing. So and the n, the x, the n is a different n. It's not the same n. There are many n's. That's what I heard in other video from Computer File. There are many n's. I think I'll put the videos actually. I'll put the links in the reference. If n is 1, then x, else x times power x, n minus 1. This should work. Unbound value power. Oh. I should have used rec. So the type is from an int to an int to an int. So if we say power 2 to the third, and it's 8. I have to sneeze. Power 2 to the 6th. 64. Power 2 to the 12th. 4096. Power 2 to the 8. 256. Okay. Wait. Can I pause? I can pause. I need to just... Okay, we're back. I'm back. Okay, that's the power. Right, let's move on. Write a function, so now number 5. Write a function is constant. which given a lowercase character in the range of A through Z determines if it is a constant. Yeah, I'm not sure what do they write. A function is constant which given a lowercase character in the range A through Z determines if it is a constant. But aren't all characters constant? This is very confusing now. Let's check with ChatGPT. Okay. So don't help me here, but somehow guide me, because I have no clue now what is meant by this question. If it is a constant. It seems my thinking model somehow jumps too soon to some kind of result, and then hence me, I don't know how to proceed. Like here I see letters which are constants. Let's approach this step by step by guiding your thinking. Understand the problem. The task asks you to write a function that takes a single character and determines if it is a constant. So what is a constant? How do you define it? In the English alphabet, a constant is any letter that is not a vowel. Why would you? What makes you think this? What do you mean? What? Why would this be implied? I had no idea. Constant, I had no idea. Non-vowels are constants. This is a great realization. What do you mean? It's okay to feel surprise. Why are consonants? Consonant. Incredible. I thought I'm seeing constant. Yeah. I guess you can notice, when you learn so slow like this, that you sometimes you tend to misread something. Yeah, maybe I shouldn't go now too deep into this. You see what you want to see, right? Consonant. Oh, I didn't see it correctly. So now that we understand that a consonant is any letter that is not a vowel, take the alphabet from A to Z, exclude the vowels, and the remaining letters are the consonants. So, okay, let's actually get back. So write a function is consonant. Will we have a recursive function? Given a lowercase character in the range A through Z determines if it is a consonant. You see, I guess there are two ways how you can approach this. You can approach this as by, well, the function should determine if any of the letters through A and Z is a consonant. So that means if I give it an A, it says no, false. Is consonant false? So maybe I could define vowels, you know, like should I do that? That's what we did actually in the example before. We defined vowels, a, e, o, u, and then I make a function is consonant, and I just say if vowel, then false, else true. I could do that. But I'm not sure now if that's the right way, what he wants. Is consonant. On the other hand, maybe I'm supposed to write everything contained within one function. Let is consonant. I guess here it's important. Maybe if it was a snake case, I could understand. Is consonant of some character x. Let is consonant x is if vowel yeah, I could define a vowel, but what if we don't? If a, yeah, we could do that what he did before, but I don't think that's like this. Wait a second. Like this. If x equals, if else equals a, or like this, I guess, or else equals a, or else equals e, or x equals e, o, or else equals u, right? Then, well, if it's one of these things, then you would do false, right? Else true. And this would be it, actually. So it's a function from char to a bool. So now if we ask is consonant, and we ask it like in A, we get a false. And then is consonant, let's say Z, and we get a true. Well, that's the same thing with yeah, maybe he just wanted us to repeat, because that's one of the examples he did before. A function is consonant. Let's see what ChatGPT would do with this. Write this in OCaml. My solution was... What was my solution? My solution was this. Wait a second. This and control. My solution was this. No, it's not. I can't. I'm just trying to copy out from the... Right, paste it in. Wait. Maybe I pressed the wrong thing. Like this. Your solution is correct in spirit, but it can be simplified and improved slightly. For clarity, let's refine it step by step. So let is consonant x. If x, yeah, then false else true. So check input range. Ensure x is in the range A to Z. Right, I didn't do it. While the problem states this, it's a good habit to validate inputs. You're right, I didn't really do it correctly. In the range, he's giving me the range. I'm giving the range and I've kind of ignored the range. It's a cheat because I'm basically just checking. I'm checking if it's not a good program because I'm just checking if it is a vowel. And if it's not, then I say, oh, that's because I imply that, yes, because there is a finite number of chars. So if it's not a vowel, then it's a consonant, but it's a cheat because what if the range is infinite or something like that? Well, it would still be true because we only have 5, vowels. Yeah, it's kind of a cheat. So check input range. Ensure X is in the range A through Z. While the problem states this, it's good habit to validate inputs. The if then else false as true pattern can be replaced with the negation operator not. Use a helper function. Instead of repeating X, consider a helper function to check if X is a vowel. Yeah, he's a cleaner version. Let is consonant X equals. Okay, well, let is vowel and oh, this is nice. But these are some symbols actually that we didn't use. Let is consonant X equals let is vowel C equals, so C, A, E, I, O, U, in X greater than A and X lesser than Z or equal to Z, and not is a vowel X. This is much better, yeah. This is much better. Because here we are actually saying it. We are saying it in X greater or equal than A. And this is a sign for the Boolean and X is less or equal than Z and not a vowel of X. This vowel and does not belong to the vowels. And then we cover the whole range. Yeah. It's a good example. You cover the range. I guess we could use that example. True, true. This version keeps your solution's logic intact, but enhances readability and robustness. Yeah, I can already see we could use this for something like maybe like a list of numbers, and here we have some kind of a condition, like even number or something, and then we check if the number belongs in the list from, let's say, 1 to 100. Else true. Or we could, like, wait a second, we could do like this. Let is what was that name? Fizzbuzz is Fizzbuzz. Let Fizzbuzz. Let Fizzbuzz X equals, let fizzbuzz n equals, if n, no, let fizzbuzz n equals, let, well, what do we have here? Yeah, I'm trying now to somehow break down the question. Is vowel C is constant? Is fizz? Well, we could do like let fizzbuzz n. Let fizz n equals, if n equals n mod 2, if n mod 2 equals 0, then fizz. So if n is even, then fizz, right? Else, well, let's not, yeah, I'm not, yeah. If then fizz, then even. Well, let's call it even fizz. Else uneven buzz. Let fizz n equals, right, in yeah, in what? So I guess we would have to do the range here. N greater than or equal than 0. Oh, look at this, it does this. Then 0 and n less than or equal than 100. And not even, not even fizz. Interesting. And even buzz. Well, it is even or uneven, right? The number would be even or uneven. It makes no sense. Yeah, I'm trying to make now this something that I'm still not ready for. I am ready, but it takes time. So the fizzbuzz is kind of, it has to define some kind of a multiple of certain numbers and then exclude everything else. Let's try like this. But what's actually else even buzz? It makes no sense, this thing. Maybe if we could just print it. Uneven. Right? It makes no sense. Even fizz. Maybe like this. And not even fizz. Yeah, this makes no sense. This will not work actually. Unused variable fizz. Yeah, I'm still not ready for this. So I wanted to, make some kind of a function that would take a range from a range to 0 to 100. And I think it goes like, it prints the multiples of 3 with, let's say, fizz, and the multiples of 5 with buzz. And everything else, it prints. Oh, we would have to actually print those numbers out. Right, up to 100. We would get it on the screen. Yeah. Maybe that's too soon, actually. That's too soon, yeah, right? A function is constant. What is the result of the expression let x is 1? Let's see, how am I doing with time? Okay. What is the result of the expression let x is 1 and let x is 2? What is the result of the expression let x is 1 in let x is 2 in x plus x? Well, the result, that's interesting because it's in. Otherwise, you would say like look at this. So let x is 1, right? And x is 1. But if we do let x is 2, x is 2. So if we do x plus x, we do 4. But let x is 1 and let x is 2 and x plus x is 4. But it's unused variable x because we didn't use the first one. Let x is 1 and let x is 2 in x plus x. Yeah, the problem, because it complains with, look at this, let x is 1. Now it makes more sense. And we go inside. Let x is 2 in x plus x. So what's happening with this one? Let x is 1, syntax error. Oh, let x is 1 and let x is 2. And x plus x. Unused variable x. Interesting. How it is unused? I think it's shadowed. So the x2 actually shadows the x1 in x. Yeah. Let's check this out. So let x is 1, a variable x is declared and bound to the value 1. However, this x is never used because it is immediately shadowed by another x. And let x is 2, a new variable x is declared and bound to the value 2. This shadows the outer x is 1, meaning that the first x is effectively inaccessible from this point onward. The x in this expression refers to the inner x. So result is 2 plus 2 equals 4. Yeah. Now the compiler gives a warning, and this refers to the outer x, right? Which is never used in the program because it is shadowed by the inner x. You can give the variables different names. Suppress the warning if intentional. Okay. Can you suggest a way of preventing the non-termination of the factorial function in the case of a zero or negative argument? Well, that's the base case, or negative. Well, factorial times factorial of 0 is 1. That would be the base case. Equals 1, and that stops, right? Can you suggest a way of preventing the non-termination of the factorial? So let rec factorial a equals, now our base case is if a equals 0, right? If a is 0, or if a is if a is, or if a is less than 0, then factorial a then 1, then just 1, else a times factorial a minus 1, right? So now we have factorial of 4, 24. And if we do, okay, factorial of 0 is 1, and factorial of minus 1 is 1. I guess that's correct. Correctamundo. Check this. Next question. Okay. My solution to next question. My solution to next question. Your solution already includes a check which prevents non-termination by returning 1 for these cases. However, the function might still accept negative inputs without warning the user that the factorial is undefined for negative numbers in most mathematical contexts. It's undefined, right? It's not 1. To improve the design, you can raise an exception for invalid inputs. Instead of silently returning 1 for negative inputs, you can raise an exception, making the behavior explicit. Use a guard to restrict the domain. Factorials are only defined for non-negative integers, so you could ensure that the function only works for valid inputs and reject invalid ones. Oh, that's the fail with. We haven't learned that. If a is less than 0, then fail with factorial is undefined for negative numbers. Else if a is 0, then 1. Else, okay, we can do that, yeah. Explicit guard with assert. Return an option type. Matches. We didn't do matching. All right. Nice. Yeah. Okay. I'm finally done with this chapter. Come on. Naming and functions. Note on notation. From now on, instead of showing the actual OCaml session, if a is 1, then 1, else a factorial, val factorial, we will usually just show the program in a box together with its type. Yeah, factorial int let rec factorial. If you prefer to compose your programs in a text editing program and copy and paste them into OCaml, you can do that too. Just make sure you end with semicolons to let OCaml know you have finished. entering the program. Later on, when we write larger programs, we will see how to load our programs from external files. Let's do this. Yeah, lecture 15, recursion. Alpha Centauri. Maybe this nostalgic synth playlist. Wait, let's try this. If you prefer, okay. Case by case. In the previous chapter, we used the condition expression if. In the previous chapter, we used the condition expression if. Then else to define functions whose results depend on their arguments. Okay, yeah, we used a lot of ifs. So for some of them, we had to nest the conditional expression one inside another. Programs like this are not terribly easy to read and expand quickly in size and complexity as the number of cases increases. It's just so far, it's interesting. I feel like with OCaml, there are just a lot of let statements, and there's something about Haskell that I still like. I don't know. I almost like want to also return to Haskell. I've been trying to learn it for so many years, and I somehow keep coming back to it. OCaml has a nicer way of expressing choices. Pattern matching. Okay, we're finally doing the pattern matching. For example, recall our factorial function. Factorial int let rec factorial a. If a is 1, then 1. Else a factorial a minus 1. Yeah, right, let's R factorial. We can rewrite it using pattern matching. Factorial int let rec factorial a match a with what? If it's 1, then 1. Ah, that's nice. It's funny that we still need this. Okay, let's turn off this thing. I think he did this so that you cannot copy and paste the code. Look at this. You can't copy and paste. Okay. Wait, I'll turn this dark reader on. Pattern matching. Wait, how long was this? 1 hour and 3 minutes. That's enough. I'm gonna watch now some lectures actually in functional programming. Yeah, okay, bye-bye.